The Binomial Coefficients Theorem. This theorem, first discovered by Sir Isaac Newton, says that the coefficients preceding the variables in binomials raised to a given power are as follows. We have the following shown on screen. The general term of this binomial expression therefore is, we have the following shown on screen. Hence, the algebraic form of expansion of the binomial expression, a plus b to the power of n, we have the following shown on screen. Where the symbol n, sigma k, equals 0, is an abbreviation that means, the sum of all terms from k, equals 0 to k, equals n. From the formula and from the definition of factorial, it is clear that the first and the last coefficients are both 1, because we have the following shown on screen. We have the following shown on screen. We observed this fact in all examples discussed so far, where the leading and the trailing coefficients were both 1. Let's prove the formula of the binomial coefficients by calculating them through the method, and eventually comparing the results obtained by all values shown in the Pascal's triangle table. For n equals 0, we have the following shown on screen. For n equals 2, we have the following shown on screen. For n equals 2, we have the following shown on screen. For n equals 3, we have the following shown on screen. For n equals 4, we have the following shown on screen. For n equals 5, we have the following shown on screen. For n equals 6, we have the following shown on screen. For n equals 7, we have the following shown on screen. If you compare all coefficients found above using the binomial coefficients formula with those in the Pascal's triangle table, you will find out that they fit perfectly. Therefore, now we have a much more powerful method for calculating the binomial coefficients of any degree. Example 1. Find all coefficients of the binomial, x plus y, to the power of 10 when written in the expanded form. Solution 1. Let's make a table for a better understanding. Since the number of terms in a binomial is 1 more than its degree, the table will have 11 rows in total, each of them representing a particular term of the binomial in the expanded form. We have the following shown on screen. Therefore, the expanded form of the binomial, x plus y, to the power of 10 we have the following shown on screen. We can generalize this approach to include all types of binomial expressions. For example, if we have to expand the binomial expression, 3x minus 2, to the power of 5, first we express 3x equals a, and minus 2 equals b, then we follow the procedure described in theory. Example 2. Expand the following binomial expressions. A. 2x minus 4, to the power of 5. B. 1 minus 3x, to the power of 6. Solution 2. A. We replace 2x with a, and minus 4 with b, based on the Pascal's triangle, or in the binomial coefficients theorem if you wish, we obtain the following shown on screen. Now, we replace back a and b with the original terms. This yields, we obtain the following shown on screen. B, we replace 1 with a and minus 3x with b, applying the Pascal's triangle method, or the binomial coefficients theorem if you wish, yields we obtain the following shown on screen. Now, we replace back a and b with the original terms. This yields, we obtain the following shown on screen. That is all for lesson 12.3.5. To continue this tutorial, please watch 12.3.6. What is a binomial when it is not in the standard form? Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.